Welcome friends. This is the first video in the course MAT 102 Vector Calculus, Differential Equations and Transforms. The first module is Calculus of Vector Functions. In this module, we will consider functions whose values are vectors. Such functions provide a unified way of studying parametric curves in 2 space and 3 space and are a basic tool for analyzing the motion of particles along curved paths. So we will begin by developing the calculus of vector valued functions. In your previous classes, you have already studied vectors. I mean your +2 classes. So a vector is usually depicted like this. It is depicted like an arrow. Now, to describe some physical quantities like, say, the speed of a wind or the velocity of a wind, you need two quantities. That is, one is the magnitude of speed and the direction of the in which the wind is blowing. So some quantities like velocity, force and displacement need the magnitude as well as its direction to describe it. For such quantities we will be using vectors. But for some quantities, say like length of an object, you just need the magnitude or the magnitude of length of that particle. There is no direction associated with it. So such particles in such quantities are called scalars, in which you only need the magnitude of that specific quantity. Examples are length, mass, temperature, etc. But for quantities like velocity, force and displacement, you need the magnitude of velocity and its direction also. So this is the importance of vectors. As you can see in this figure here, vectors are usually depicted by an arrow which starts at the origin 0, 0 to the to the point with coordinates v1, v2. So this will be the point with coordinates v1, v2. So this length of this ray will give you the magnitude of the vector, and this direction in which the arrow is pointing usually gives you the direction of that given vector. So many physical quantities such as area, length, mass and temperature are completely described once the magnitude of the quantity is given. Such quantities are called scalars. Other physical quantities called vectors are not completely determined until both a magnitude and a direction are specified. For example, winds are usually described by giving their speed and direction, say 20 km per hour northeast. The wind speed and wind direction together form a vector quantity called the wind velocity. Other examples of vectors are force and displacement. Okay, so in this module we will be studying vector valued functions. So how is a vector denoted? Usually in two space, that is in two-dimensional space, a vector is denoted like this: v equal to v1i plus v2j, or it is simply denoted in ordered pairs like this, say v1 comma v2. Now in three-dimensional space, a vector is denoted like this: v1i plus v2j plus v3k, where, or in other notation, it is denoted in ordered pair like this: v1, v2, v3, using these brackets. Now in 3 dimension, you know the unit vectors, say in these directions, you can just call it as, say, I vector, j vector, k vector. Okay, these are the unit vectors in their specific direction, and along with v1, v2, v3, they will give you any specific vector in a three-dimensional space. Now moving on to vector valued functions. Functions which produce vectors as output are called vector valued functions. For example, in 2 space, say suppose I am writing a vector like this: r of t is equal to x of t into I plus y of t into j. So this is a vector valued function in two-dimensional space because the output of this function is a vector like this. That is why it is called a vector valued function. Now the input variable is t. So this representation, if you write it in bracket notations, it will be x of t comma y of t using these brackets. Now this is, you can associate this with the parametric notation also. You see, it is all the coordinates are defined using a single variable t. So it is similar to the parametric equations that you have already studied. Now in three-dimensional space, in 3 space, a vector valued function will be like this: r of t equal to x of t, y of t, z of t, or in other terms it will be x of t into I plus y of t times j plus z of t k. Now these x of t, y of t, z of t, these are called the components of the function. As an example, you can consider this vector valued function r of t equal to t into I plus t square into j plus t cube into k. Here t, t square and t cube are called its components. This is x of t, this is y of t, t square is y of t, t cube is z of t. So x of t is t square, y of t is x of t is t, y of t is t square, z of t is t cube. These are called the components of this vector valued function. Now the figure that you see here is the graph of the vector valued functions that we have just described. That is ti plus t square j plus t cube k. Now usually the domain of a vector valued function r of t is the set of allowable values for t. For an example, you consider this given vector valued function here: r of t is equal to log mod t minus 1 I plus e raised to tj plus root tk. Now its components are log mod t minus 1, e raised to t and root t. Now let's find the domain of these individual functions. That is domain in here, domain by domain we mean the set of all allowable values. Now mod t minus 1, it always takes positive values. So log is defined for all those values except when t minus 1 becomes 0. So t minus 1 equal to 0 means t equal to 1. So log mod t minus 1 is defined for all values of t except for t equal to 1. So you just remove t equal to 1 from the real line. So minus infinity to 1, union 1 to infinity. This is the domain of log mod t minus 1. Now the second component is e raised to t. Now e raised to t is defined for all values of t. So the domain is minus infinity to infinity. Now the third one is root t. The third component is root t. Now root t is defined only for positive values of t. So the domain is closed interval 0, open interval plus infinity. Now the domain of our function r of t will be the intersection of the domain of its individual components. So you take the intersection of the domains of all these individual components and then you will get the domain of r of t. So the domain of r of t is intersection of all these. So here you only have 0 to infinity. So in one case you only have say 0 to infinity. So this is one case, and in the other case you have say minus infinity to 1. So here this part is there, minus infinity up to 1 is there, 1 is avoided in one case. Okay, and in the third case you have minus infinity to infinity. So the intersection will be from 0 to infinity except 1. So that is the domain of r of t. So the domain of r of t is the positive real axis except t equal to 1. So by the domain of, or by the natural domain of a vector valued function, we mean the set of all possible values of t for which the function is defined. Now, moving on to the graphs of vector valued functions. If r of t is a vector valued function in 2 space or 3 space, then we define the graph of r of t to be the parametric curve described by the component functions of r of t. Okay, so for example, if we have, say, some function like this, then say r of t, suppose I'm having some function r of t equal to, say, x of t, y of t, z of t, then the graph is actually the graph of r of t is the graph traversed by the equation or by the curve with the parametric equation x of t, y of t, z of t. So what you have to do is you draw the vectors at, so suppose if you are imagining it like that, you draw the vectors at each point. Says this is the vector r of t at that point, and suppose r of t is something like this at this point, say r of t1, and here it is, say, r of t2. So the graph is of r of t is the graph which is traversed by the tip of all these vectors. Okay, so for an example, you just consider this function here, r of t equal to cos ti plus sin tj. So here x of t is cos t, y of t is sin t. So you know in parametric equations, x equal to cos t, y equal to sin t represents a circle. So the graph of r of t equal to cos ti plus sin tj is the circle that is given here. It is this circle. Okay, so what you have to do to graph a vector valued function, you just write down its components x of t, y of t, z of t, and you will get the parametric equation of the graph of that vector valued function. You can use softwares to plot such functions. Now moving on to vector form of a line segment. So here we will be discussing the 2-point vector form of a line. So if r0 and r1 are vectors in 2 space or 3 space, then the line passing through the points r0 and r1 can be expressed in vector form as r equal to 1 minus t times r0 plus t times r1. That is, suppose you have two vectors, say this is r0, and suppose you have another vector, say this is r1, then the line segment joining these two vectors, or the vector in that sense joining these two vectors, these two endpoints, will be given by r equal to 1 minus t into r0 plus t times r1, where t varies between minus infinity to infinity. Okay, so this will give you the line segment joining r0 and r1. Now here specifically, if we restrict t between, say, 0 to 1, suppose if I restrict t between 0 to 1, then I will get the line segment joining r0 and r1. Okay, so I'll repeat once again. If we restrict the t values between 0 and 1, we will get this line segment joining r0 and r1. And suppose if we take t to be from minus infinity to infinity, then we will get the line passing through r0 and r1. Then we will get the line passing through r0 and r1 if we take t to be minus infinity to infinity. And suppose if we are taking only, say, the values for t as 0 to 1, if we restrict the values of t to be between 0 to 1, then we will get the equation of the line segment joining r0 and r1. Okay, now moving on to the derivative of a vector valued function. If r of t is a vector valued function, we define the derivative of r with respect to t to be the vector valued function r dash, given by r dash of t equal to limit h goes to 0 r of t plus h minus r of t by h. So this definition is similar to the definition of the derivative that you have studied in your earlier calculus classes. So f dash of x is usually defined as limit h goes to 0 f of x plus h minus f of x by h. So similarly here also it is defined but like this, but we will not be using this definition as such to find derivatives, because the derivative of a vector valued function will just be the derivative of its individual components, that is x dash t, y dash t, z dash t. That will give you the derivative of r. Now the geometrical interpretation of the derivative. So if r is this vector that you see here, if r of t is this given vector here, then the derivative of r of t will actually be the vector which is tangential to your radius vector r of t. Okay, so r dash t geometrically will be tangential to the graph of r of t at that given point r0, or at the point in which you are trying to find the derivative. Okay, now we will do an example here. So r of t, suppose the function r of t is t square I plus e raised to tj minus 2 cos pi t k, then r dash t will be just the you will get r dash of t by just differentiating its individual components. So d by dt of t square I plus d by dt of e raised to tj plus or minus d by dt of 2 cos pi t k will give you the derivative of r dash of t. Now d by dt of t square is 2t, d by dt of e raised to t is e raised to t, d by dt of 2 cos pi t is minus 2 pi sin pi t. Okay, so the final answer here, the r derivative of this vector valued function is 2ti plus e raised to tj plus 2 pi into sin pi t k. So to find the derivative, if suppose r of t is given like this, x of t into I plus y of t into j plus z of t k, then its derivative r dash of t is just d by dt of x I plus d by dt of y j plus d by dt of z k. Okay, so you can find derivative like this, and you already know how to find derivative of functions of a single variable t. So you use the formulas that you've already studied and just find the derivative of such a vector valued function. And the derivative follows all the rules that you have already studied. That is, derivative of constant is 0, derivative of constant times a vector valued function is equal to, you can take the constant outside. Okay, that is, if you are having d by dt of k times r, you can just take the k common outside and just take the derivative of r of t, and the derivative of sum of two vector valued functions is the derivative of the individuals, is the derivative of the sum of the individual functions. Okay, so d by dt of r1 plus r2 is equal to dr1 by dt plus dr2 by dt. Similarly, the difference between two functions also is equal to the difference of the derivatives of the individual functions. Now if you are having product of two functions, you will have to use the product rule. So first function into derivative of the second plus derivative of the first function into second function. Now suppose if we have a vector valued function, how to find the tangent to that function at a given point. Okay, so let r0 be the value of that function at the point t0. So r0 is r at t0 and v0 is v at t0. So v at t0, or this is actually equal to r dash at t0. It is equal to r dash at t0. Then the tangent line to the graph of r of t at r0 is given by r equal to r0 plus t times v0. So suppose if you have to find the tangent to a vector valued function at a given point, then what you have to do is you find the derivative function, say r dash at that point, r dash at t0. So that is what we are going to call as our v0, and you find the value of that function at that point. So r of t0 is r0. So r0 plus t times v0 will give you the equation of the tangent at that given point t0. Now we will do an example here. Find parametric equations of the tangent line to the circular helix x equal to cos t, y equal to sin t, z equal to t, where t equal to t0. So they are not giving you the point t naught. Instead, they are asking you to find the tangent at any arbitrary point, say t naught. So t naught is a point, and use that result to find parametric equations of the tangent lines at the point. So what do we have to do here? We have to find the tangent to this function. Say r of t is equal to cos ti plus sin tj plus tk at the point t naught. We have to find the tangent at the point t naught. So r, you write down your given function, find its find its value at the point t naught. So at the point t naught, r of t is cos t sin t at the point t naught is cos t naught sin t naught t naught. So this is cos t naught I plus sin t naught j plus t naught k. Now you find the derivative, that we are going to call it as v naught, so r dash of t naught. So first you find r dash and then substitute the point t naught, then you will get r dash of t naught. So derivative of cos t is minus sin t, derivative of sin t is cos t, derivative of t is 1. Now you substitute the point t naught, then you will get sin t naught, cos t naught, and then 1. So this is your r naught and v naught. Now you just substitute all of these quantities in this given equation, r naught plus t times v naught. So that will be equal to cos t naught sin t naught t naught, that is the value of r naught, plus t times minus sin t naught I plus cos t naught j plus 1 times k, that is the value of t. Now what we can do here is we can take the sum of this individual components and then write it here. So cos t naught plus t minus t times sin t naught, that is the first component here. Then sin t naught plus t times cos t naught, that is the second component here. Then t naught plus t times 1, that is t naught plus t is the third component. Now if you are this is the general equation to the tangent at the given point t naught. Now they have specifically asked you to find the tangent at the point pi. So just substitute t naught equal to pi, you will get the tangent, that is you will get the equation of the tangent at the point pi. So cos pi minus, so at pi it will be equal to say cos pi minus t times sin pi. Now sin pi is 0, cos pi is minus 1, so you have it is equal to minus 1. Then the next value is sin pi plus t times cos pi. Remember, t naught is the point, t is the variable. Okay, so sin pi is 0 and cos pi is minus 1, so you have minus t here. And the third point is t naught plus t, that is pi plus t. So that is the third component. So the tangent to this vector at the point pi is minus 1i minus tj plus pi plus t times k. Now instead of t naught, if they had directly asked you to find the tangent at the point pi, then what you can do is you find r of t. So substitute t equal to pi. So you will have cos pi sin pi pi. That is your r naught. Then v naught is r dash at t naught. So r dash is minus sin t cos t 1 at the point t equal to pi. So you find out at the point pi, so it is minus sin pi cos pi 1. That will be the value of v naught. So r naught plus t times v naught. This plus t times the second quantity will give you the equation of the tangent at that given point. Now moving on to another question. Here we have, let r1 equal to tan inverse t I plus sin t j plus t square times k, and r2 equal to t square minus ti plus 2t minus 2j plus log t k. The graphs of r1 and r2 intersect at the origin. Find the degree measure of the acute angle between the tangent lines to the graphs of r1 and r2 at the origin. So they have told you that these two vector valued functions intersect at the origin, and they're asking you to find the acute angle between them. So you have already studied in your smaller classes, that is, if you have two curves like this, says I'm calling it C1 and C2, how do you measure the angle between these two curves? The angle between these two curves is actually the angle that the tangent of these tangents make at these two points, right? So suppose this is the point of intersection, draw the tangent to the curve C1 at that point, and then you draw the tangent to the curve C2 also. So the angle, this angle that the tangents make, that is called the angle between these two curves. So what you have to do to find the angle between two curves, you draw the tangents to these two curves at the point of intersection. So say this T1 is one tangent, say T2 is the other tangent. So T1 is the tangent to C1 at the point of intersection, say P, and T2 is the tangent to the curve C2 at the point of intersection P. Then the angle between these two tangents, theta, is called the angle between C1 and C2. Similarly here we are having two vector valued functions. So what we are actually going to do is, suppose we are having two vector valued functions r1 and r2, then you draw the tangential vectors at the point of intersection. So the tangential vectors here, suppose this will be say r1 dash at that point, and the tangential vector here will be r2 dash. Okay, now the angle, acute angle between r1 dash and r2 dash is called the angle between these two vectors or vector valued functions. So we'll solve this question using that concept. So the graph of r1 of t passes through the origin at t equal to 0, where its tangent vector is given by. So it is given that this point of intersection is the origin. So what you have to do, you just find r1 dash at the point 0, 0. So sorry, at the point 0 at t equal to 0. So r1 dash you find at the point at the origin. So passes through the origin at t equal to 0. So that is also a point that you must understand. So that is, I'll just illustrate one thing and then we'll continue. Say the first function is r1 of t equal to tan inverse t plus sine t j plus t square k. Now they are saying you have to find the value of t for which it passes through the origin. That is, this is suppose equal to 0, 0, 0. Then what is the value of t? So when this is t square equal to 0, third component equal to 0 implies t equal to 0. And the second last component sine t equal to 0 also means t equal to 0. So and tan inverse of t equal to 0 means t equal to 0. So the value of t at which the function passes through, or at the value of t for which the function value becomes 0 at all these components is t equal to 0. So here the graph of r1 of t passes through the origin at t equal to 0. So when t equal to 0, the graph passes through the origin, or the graph or the value of that vector is equal to 0, 0, 0. Similarly, okay, now we'll keep it there and then we will find r1 dash at that point. Okay, so we'll find r1 dash at the point 0, 0 or t equal to 0. Okay, so r1 dash is, you find the derivative of these three components. So tan inverse t derivative is 1 by 1 plus t square. Sin t derivative is cos t. T square derivative is 2t at the point t equal to 0. So when t equal to 0, 1 by 1 plus 0 is equal to 1 and cos 0 is equal to 1. 2 times 0 equal to 0. So r1 dash at 0 is 1, 1, 0. Now we have to find r2 dash at 0, 0. So we have to find out not at 0, 0, at 0, 0, 0. Now we have to find the value of t for which this function becomes 0, 0, 0, or the value of t for which r2 passes through the origin. So r2, what was r2? r2 is t square minus ti plus 2t minus 2j plus log tk. So this is your r2. Okay, this is your r2. Now what is the value of t for which it becomes 0, 0, 0? That is what we have to find out, or in other terms we have to find out the value of t for which it passes through the origin. Now for the simplest case, let's take this value. So 2t minus 2 equal to 0 implies t equal to 2 or t equal to 1. So when t equal to 1, the graph of that function will pass through the origin. Similarly, now let's check that same value. When t equal to 1, log 1 equal to 0. So log t equal to 0 implies t equal to 1. Now here you will be having two values of t. Now t square minus t equal to 0 means t into t minus 1 equal to 0. So t equal to 0 or 1, but we have found the common value, that is t equal to 1 is the common value for which all the three components x of t, y of t and z of t becomes 0. So the second vector valued function R2 passes through the origin at t equal to 1. Okay, this is how you have to find the value of t at which the R2 will pass through the origin. Now we have to find R2 dash at 1. Now R2 dash, now t square minus 1, that is the first component, so its derivative is 2t minus 1. Second component is 2t minus 2, its derivative will be 2. Third component is log t, its derivative will be 1 by t. Okay, now find all these find the value of all these components at t equal to 1, and that will give you R2 dash of 1. So when I substitute t equal to 1, I'll get 2 into 1 minus 0, sorry, 2 into 1 minus 1, it is 1. Now the second value is 2, it is a constant, there is no t there. Third value is 1 by 1, which is equal to 1. So this is the derivative, this is r1 dash at 0, this is r2 dash at 1. Now we know the angle theta between two tangent vectors satisfies this given property here, that is, suppose you have two vectors, say a and b, then cos theta is equal to a dot b by norm a into norm b. We know this property, that is cos theta will be, that is, if theta is the angle between two vectors a and b, then cos theta equal to a dot b by norm a into norm b. Now what is norm a? For any vector, say suppose the vector is like this, a equal to say xi plus yj plus zk, then by norm a we mean the distance from the origin, that is x square root of x square plus y square plus z square. This is what we mean by norm a. Now using that we will find cos theta. So cos theta is equal to vector r1 dash at 0 minus vector r2 dash at 1. Sorry, not minus, dot product. Okay, so a dot b by norm a into norm b. So a dot b, you know how to calculate the dot product. So 1 into 1, that is 1, then plus 1 into 2, that is plus 2, plus 0 into 1, that is plus 0. So 1 plus 2 plus 0. So a dot b is 3. Now the norm of 110 will be square root of 1 square plus 1 square plus 0 square, which is root 2. Now norm of 1 to 1 will be square root of 1 square plus 2 square plus 1 square, which is equal to 1 plus 4 plus 1, that is root 6. Now this will be 3 by root 12. Now root 12 is 4 into 3, square root of 4 into 3 or 2 root 3. So the output will be root 3 by 2. So cos theta is root 3 by 2. That means theta is equal to 30 degree. Okay. So this is how you have to find the angle at the point of intersection between two vector valued functions, or between the graphs of two vector valued functions. Okay then, thank you.